All right, so today I'll be talking about atomic force microscopy. First discovered in 1986, AFM is used as a characterizing tool for nanostructures due to its easy operation and accessibility. It is widely used due to its minute intrusion to measure electrical and optical properties associated with topographic data. This is how our shared facility at Benedum in FCF looks like. Okay, so in order to characterize a sample, it scans on sample surface using sharp tip. The tip has to be sharp because to measure high lateral resolution for a topographic image. The tip is attached to a cantilever, which is then attached to a probe or chip, which is not shown here actually. The cantilever is oscillated near its fundamental oscillation frequency by a piezoelectric actuator in response to the voltage applied. SHO predicts the motion of the cantilever. Okay, so in overall, the setup of an AFM somewhat looks like this. Um, the interaction between the tip and the sample surface, which is placed on a movable platform, generates change in the oscillatory behavior of the cantilever, causing small phase difference, which then causes the deflection to occur. The change in deflection causes the laser to reflect at the photodiode. Uh, so at the photodiode, which thereby it results in taking of an image. So the tip sample interaction can measure a lot of properties and including amplitude, height, phase angle of vibration. The amplitude is measured using this formula where Zi is the deflection of the cantilever. The height of the sample surface is measured using voltage using voltage that is applied to maintain the cantilever amplitude. And the phase angle of vibration is the time lag or lead between the mechanical response between the sample and the tip, where so all of these deflection of cantilever, which I talked a lot earlier, is the deflection of the cantilever is helps to find the force concerning which the formula of which we get from the Hooke's law, where F is the force between the tip and the sample surface, the Kc is the spring constant, and Z is the deflection of the cantilever. Okay, so the common techniques that are used in AFM is AC mode imaging, which is used for soft surfaces to reduce frictional lateral force. And the other one is contact force mode, which is for hard surfaces. The name suggests, in contact mode, the tip is in constant contact with the surface, and it generates a topographic map by applying the required voltage at Z piezo to maintain a constant deflection. Uh, on the other hand, the AC mode imaging is somewhat tapping, so it touches the surface at times and it goes away from the surface at times. So it's not in constant contact with the surface. A very well-known type of AC mode imaging is Kelvin Pro Force Microscopy, KPFM, where the tip is conductive because it's scanned over the surface to record the electrostatic potential map. Here, the distance between the probe and the sample surface is periodically varied to produce a frequency-dependent capacitance, which in turn generates AC voltage, which is proportional to the voltage difference between the probe and the sample. So instead of measuring the AC voltage directly, a DC voltage known as the contact potential difference is typically applied to counteract the response. This contact potential difference is of the actual importance. This is what it is meant. This is what is measured and will help us in whatever I'll be discussing further. So it's of good importance, I would say. Anyway, so the first example is where Ghosh et al. Investigates interfacial effects of chiral molecules on ferromagnetic substrates using Kelvin probe measurements to study the surface potential changes. Um, they examined ferromagnetic thin film electrodes coated with self-assembled monolayers of chiral molecules, and they found that electron penetration occurs from metal to the chiral molecules. There are certain goals of the experiment, which includes uh, understanding the electron dynamics in the spintronics and the quantum information technologies, to understand what is going on at the spin interface, the and how chiral molecules regulate the electron spin density at the interfaces, and how cis can have an effect that imposes spin dependent constants on the above points. So the experimental results of this experiment shows that after deposition of chiral organic SAMs on ferromagnetic substrate, magnetization, if magnetization is set parallel or anti-parallel to the surface normal, the KPFM study was done to understand spin-dependent charge injection. And upon application of oscillating electric field to probe the charge injection dynamics, it was seen that the CPD that I mentioned earlier varies with respect to molecular chirality and magnetization direction. So both of them. Therefore, the observed effect definitely originates from the spin-selective electron interaction at the interface. The CPT distributions show that the D and L, the two isomers, are of equal and opposite in magnitude, which is shown in the like the figure as well, while the achiral one doesn't show any significant change. Okay. So there were it in the paper. It also is mentioned how AFM was used to understand that the spin polarized electron density dissipates with distance. As in, if the thickness of the gold substrate, which is used here, is increased, then the spin polarization is decrease. The spin polarization basically decreases with the increase in the thickness of the gold substrate. All right. Okay. So in the second example, Capon et al. Investigates the chiral discrimination in biosystems using atomic force microscopy to measure enantiospecific interactions. It showed that the chiral discrimination originates from space inversion symmetry breaking, which in turn indicates that there is some electromagnetic implications. These two phenomena that described here were not typically captured in the traditional spectroscopy um, used in the past. Um, Here, they highlighted that van der Waals interaction and exchange interaction both are involved to make both contribute to to molecular symmetry breaking and spin orbit interaction. Okay, so in the experimental details, they have mentioned that the AFM tip was functionalized with chiral oligomer and was then used to measure intermolecular force between the tip and the double-stranded DNA, which has oxidative damage. The measurement showed location dependent of spin-based interaction. Therefore, it was able to identify damages at large distances. It also showed that the numerous force versus distance curve which was taken showed pulling events, and the different mean pulling force profiles for up and down magnetization indicates that spin selection between the chiral oligopeptide and the double-stranded DNA, and the observed force dependence on magnetization suggests that spin polarized electrons play a role in interaction between the oligopeptide on the tip and the adsorption of the DNA. It was also seen that redistribution of charges within the DNA on ferromagnetic substrate was observed. That is, the amount of charge penetrating into the DNA from the ferromagnetic substrate depends on magnetic or spin orientation of the emitted electrons and the oxidative damage. It is crucial to emphasize that the spin-based recognition, I'm sorry, it is crucial to emphasize that the spin-based recognition mechanism is effective over distances much greater than what was predicted in the standard exchange force calculations. So in conclusion, AFM is a vital tool for nanoscale probing. The two main methods that I have discussed here are AC mode imaging and contact mode imaging. In the AC mode imaging, the Kelvin probe force microscopy studies tells us about the spin dependency, and in the other one, it gives the spin insights. It gives insights about the spin selectivity. That is how chirality and magnetic field work hand in. How chirality and magnetization work hand in hand. Therefore, AFM will help produce essential spintronic devices in future, which will be of great help for providing energy efficient devices. Thank you.